Professor Shankar,
Yes.
thank you so much for doing this interview. Your book on quantum mechanics is widely considered to be a very clear explanation of the topic. So, what do you think are the biggest challenges students face when they are learning quantum mechanics?
Okay. So the challenge for me when I was learning quantum mechanics was there are lots of mathematical results, then there are physical results. And when it's taught, people don't separate mathematical theorems from physical postulates. In Newtonian mechanics, you don't have the problem because mathematics is calculus, everybody knows that. Just give the laws of Newton and you solve any problem you want. In quantum mechanics, when you try to state the fundamental rules, they involve vector spaces and operators. People don't know that. So I decided when I was, just after I got my PhD, I was postdoc at Harvard, I said, I would like to teach the subject the way I would like to be taught. So one summer, I was asked to teach in the summer school, and I taught in the summer school. One of my students from there is a professor here. His name is Doug Stone. And he was a very active fellow in my class, and he kept me honest. And it was supposed to be 1 hour long, but it was 3 hours long because Doug kept asking questions. But I wanted that. So I started by explaining the mathematics first, all the results you need. Then I gave some examples of the mathematics in classical mechanics, so you know how to apply them. Then I simply said, here are the postulates of quantum mechanics.
Yeah.
Now, in principle, you can tell the students to go home. In practice, you have to guide them through how to apply it. So the rest of the semester spent applying those postulates to solve a whole variety of problems. That's what I did in that course. Then, when I came to Yale, I wanted to write a book based on those lectures. Doug encouraged me to do that too. And I wanted to write a book. And it was not easy to get a publisher because they said, we already have books on quantum mechanics.
Yeah.
So I said, you don't have my book on quantum mechanics. They said, well, it's too many books. So finally, I found a publisher called Plenum Publishers. They're mainly journal publishers. They're not textbook publishers, but they liked this book and they published it in 1980 and it's still going strong.
Wonderful.
Yes.
And students are using your textbook during your course on
They have no choice, unfortunately, because I'm teaching it right now.
Yeah.
But when other people teach, they're free to do what they like. Some of them use it, some of them have other books they like. I don't try to influence that. Also, my book has to be taught with some care because it's got a lot of material. You just cannot teach it in 1 year if you try to teach everything.
Yeah.
So you have to decide what you want, what you don't want. And there are some books where you don't have to throw anything out. It is just the right amount for 1 year. So they will use that book. But others may find it's worth the investment to teach it this way. So sometimes they use this one.
I see. Quantum mechanics can seem paradoxical. So was Richard Feynman right when he said that no one really understands quantum mechanics? Yes. So do you think that Feynman was perhaps one of the greatest teachers on quantum mechanics?
Yes. Well, I don't like his books that much because he thinks that everybody is as smart as he is. Sometimes the more mundane textbooks tell you how to do it.
Yeah.
Feynman tells you how he can do it, but not how you can do it. So you go away with an impression you know it, but you don't. But one thing I learned from him was the double slit experiment is the key to quantum mechanics. I still remember that. So I start my course when I finish with mathematics and review of classical mechanics with the double slit. So I cannot tell them all the experiments that showed the need for quantum mechanics, black body radiation. You don't need all of that. The double slit will tell you in the simplest terms, classical mechanics cannot hold. So you confront the students with that fact and say, look, forget the theorem, forget the results. This is what happens. I've given some public lectures on quantum mechanics where I tell them, look, I cannot tell you the mathematics, but I can tell you the phenomenon. That's a certain phenomenon. Namely, you cannot tell which slit a particle goes through. That's all it means to us and to you. We are no more comfortable with that than you are, but that is the new part of quantum mechanics. So I do the double slit, then I tell them how that paves the way for the new quantum mechanics you need. It cannot be deduced, but it's a good way to start. Then I just give the axioms. Then I develop many examples.
How did quantum mechanics arise from nothing, basically?
Yes. So general relativity was very unusual. It arose from one man's brain, from his desire to generalize the special theory of relativity, and he struggled for a long time. By the way, many occasions he thought he had found the right answer. He was very convinced, this is it. But it was wrong. But he was smart enough to accept that it was wrong. And finally, the final version came out, which is what we accept today for GR. And everyone agrees that's a one-of-a-kind discovery because it was so far ahead of its time in terms of phenomena. Even special relativity didn't have many phenomena that demanded. So there was some experiment that showed that the kinetic energy is not mv squared, but something else. But for GR, there's no reason at all to abandon it other than satisfaction of your curiosity. But for quantum mechanics, it was quite different. There were lots of experiments which made no sense. And I'm so amazed with the pioneers of quantum mechanics and how from that mess they extracted this perfect theory. I love teaching it. I never get tired of teaching it. When I came to Yale, I requested that I be assigned quantum because I was writing this book. And then after writing the book, I stopped teaching it because people come to the class with the book and they want to see how well I know my own book.
Yeah.
But then I was induced later on to step in sometimes when there was nobody else or no one wanted to teach that course. But then, what was I saying? I'm an old man who forgets what I was.
Yes, you said that GR was before quantum mechanics.
But yeah, quantum mechanics were driven by experiment. Yes. And the experiments are very messy. And once Wolfgang Pauli said that he was so miserable, and someone said, why? He said, I'm thinking about the anomalous Zeeman effect. How do you think I should look? So there was very complicated spectra. And my hero from that period is really Heisenberg.
Okay.
I can tell myself on a good day, I would have discovered this and I would have discovered that. I can never imagine discovering what he did. There is no path to where he got there and where he started.
Right. But would you say that maybe Schrödinger contributed more to quantum mechanics than Heisenberg?
He brought out a version everybody could understand. I mean, look, you cannot derive the Schrödinger equation. Neither could Heisenberg derive matrix mechanics. But if you get the Schrödinger equation, you can find nowadays, a good undergraduate who can solve the hydrogen atom or the harmonic oscillator. With matrix mechanics, besides the oscillator, only Pauli could solve the hydrogen atom. It's tool de force to solve that. So, but Schrödinger did find in his own way a method that relied on differential equations that everybody was comfortable with. Matrix mechanics was not known. They did not. Heisenberg did not know that what he wrote down as an array was a matrix.
I see.
Yeah, Jordan is the one in Max Born's group who I think knew it as a matrix.
Right. And is it true that Einstein isn't the father of general relativity? Or he's the father, but he's not the creator of GR?
I think he is. Who else do you think?
Newton, maybe. Isn't he the grandfather of GR? No?
No, that fathers and grandfathers, yes.
Yeah.
I mean, Galileo, when I give lectures, I say, of relativity principle.
Yeah.
Yes. GR is Einstein's baby.
Okay.
But the relativity principle was first enunciated by Galileo.
I see.
About going on a ship and not observing its state of motion. But then Newton's laws told you why that is true. Under what conditions you cannot tell you're in a moving frame. But then Einstein went and extended relativity from mechanics to everything.
I see.
So yeah, Galilean relativity and Newtonian relativity says if you're inside a closed train, you cannot tell if it's at rest in the platform or moving at constant velocity. You cannot tell by any mechanical experiment. And you can prove that F equals ma, if it's valid at the station, is valid in the train. But it was not true about other physics problems. So Einstein is the one who said it has to be true for everything.
See. Do you prefer GR or quantum mechanics? So which theory do you find more beautiful and more satisfying?
Right. I'm not sure because, it's like asking somebody whose music you like more. But I think I understand quantum mechanics better than I understand GR. I'm not an expert on GR. I know the ground rules, but I have my colleagues who can do all kinds of difficult calculations. It can get very nasty. For me, when I was growing up, relativity, especially GR, was not mainstream. Besides the three famous tests, there was Shapiro's experiment. There was not many experiments that required this thing at all. But now it is quite the opposite. They are in a very enviable position of so many experiments that require us to use this theory.
Yeah, and one of the most famous substance of quantum mechanics is quantum entanglement. So Einstein said that it is a spooky action at a distance. So what do you think about quantum entanglement, and was Einstein right when he said it?
Well, you can certainly agree that it is spooky. It is spooky, and it seems to work outside the light cone, the effect. For that reason, you may say it cannot be true.
Yeah.
But it is. We know experimentally that action at a distance is present. So it's very difficult to accept that. But one thing about physics is you don't have to like it or love it. You just have to suck it up. If that's what experiment says,
I see.
you have to learn to live with it.
I see.
So entanglement is still mysterious, but people like Susskind try to find a way to use GR to understand the entanglement between two objects. They got a wormhole connecting this object to that object, so there's less mysterious. But to me, a wormhole is already mysterious. I don't think it helps me understand that.
Right. And wave-particle duality is one of the cornerstones
Yes.
of quantum mechanics.
Yes.
Is there a way maybe to find a unified framework for waves and particles?
Like Donald Trump likes to say, it is what it is.
Okay.
So you cannot try to use the old vocabulary to explain a phenomenon like quantum mechanics.
Yeah.
So you just have to accept things the way they are and find the most complete way to predict the result of any experiment. You may not like the language that is used, that you use this sometimes and use that sometimes, but you should be very pleased that in any occasion you know what approach to use to explain the experiment.
Yeah. Do you think there is a philosophical limit to our understanding of quantum mechanics?
You know what? I used to be an engineer before.
Yeah.
So I don't interest myself in anything philosophical.
Oh, that's okay.
When I say quantum mechanics, I'm like a car mechanic. I want to know how to use it.
I see. I see.
I just wanted to teach my students, this is how you use it. When they're older, they can worry about, is this the way to do it? Are there better ways? Is it complete? Is it incomplete? I didn't spend much time doing that, but I have a lot of respect for people who question that. Because I thought it was a finished subject, but look at the work of Bell. He showed that it was not finished. There are still a lot of things in quantum mechanics that we didn't appreciate, how bizarre it was.
Do you think that quantum mechanics is the most complex, the most perfect mathematical formulation we have in physics nowadays?
Well, it certainly, but by perfect, I don't know what one wants. First of all, I thought relativity is very beautiful when I first learned it as a teenager. Then I read quantum mechanics, and I was again impressed with how beautifully the mathematics is tailor-made to explain quantum mechanics.
Yeah.
To me, I'm not a very religious man, but that's the closest I come to being religious. That this invention of the humans, namely matrices or differential equations, are the language used by nature. And in fact, the only language we can communicate with nature is by solving those equations. When you solve an equation for the hydrogen atom, it makes a prediction. Nature has to obey that prediction.
Yeah.
Why? It didn't have to obey it, but it does. So who's this thing we call nature that ensures that? I don't know. But there is some consistency in the world, which is to me amazing, and the fact that we are able to make a prediction in that world.
And do you think that mathematics is invented or discovered? there is also one
Yes,
philosophical
it's a
question.
great question.
Yeah.
Look, I think it was discovered.
Mm-hmm.
I find it hard to believe things you invent can be so consistent. Also, when you invent something, it may have no bearing on something else somebody invents. But if it's already there as a superstructure, then what happens in this can affect that. For example, in proving Fermat's theorem, Andrew Wiles had to bring together so many different results from so many parts of mathematics. I don't think humans could have constructed from pure imagination that construct, but those relations I like to think are always there.
I see. Can you please explain the fundamental concepts of quantum field theory and how they differ from quantum mechanics?
Okay, so quantum field theory is used in the old days. Quantum field theory meant relativistic quantum mechanics of elementary particles. But now it's a broader definition. Field theory is the theory of infinite number of degrees of freedom, one for each point in space. And quantum field theories is when the degrees of freedom are quantized.
Okay.
So a good example is electromagnetism, where at every point in space, you have a vector potential and a scalar potential. They are the degrees of freedom, classically. Then need a quantum theory where these are elevated to operators obeying some kind of uncertainty principle. And that is the quantum field theory of the electromagnetic field. You need the equations of motion for any theory, and that comes from Maxwell. So field theory originally was always relativistic field theory, but the Russians started using it. For example, Abrikosov and company started applying the techniques of Green's function and so on to condensed matter physics and many body physics.
Okay.
And many body, for us, many really means infinite number of particles. And in that limit, you need the mechanism of field theory, but not relativistically constrained. It's non-relativistic field theory.
I see. And what are some of the biggest challenges or unresolved mysteries of quantum field theory nowadays?
Let's see. For a while, there's a big mystery on why does nature have these wonderful renormalizable interactions? Why is the world renormalizable? How come these infinities all magically cancel? That used to be a big mystery.
I see.
But Ken Wilson took the mass mystery out of it completely. He shows that these infinities are artificial and they must, first of all, you don't need to have renormalization in a field theory. You can have renormalization in a non-relativistic theory with finite number of degrees of freedom. So it just means that the theory is defined with a cutoff. For a condensed matter, the cutoff can be lattice spacing. And that's a given cutoff. It's not negotiable. But what if you want to do physics at length scales much bigger than the lattice spacing? Can we use a more coarse lattice to describe that same physics? You can, because if you don't ask questions smaller than your lattice spacing, you can. But that new theory will have different parameters. And that is how we understand renormalization.
I see.
Nothing to do with infinities. If you change your cutoff and you want to get the same answers, you have to change the input numbers.
I see. There are several interpretations of quantum mechanics. Some of them are Copenhagen interpretation, many worlds. Which interpretation do you find the most attractive one?
Well, I cannot comment on them because I know only one. I only know the Copenhagen interpretation.
Okay. So
I've tried to read. Now that I have a permanent job, I can have the luxury of thinking about these things.
yeah.
But they go over my head. I'm not sure what the point is. I'm not sure why the many world interpretation is any more satisfying than the Copenhagen one.
I see. So what do you think will be the most important or exciting area of research in physics, just in general, over the next decade?
Let's see. So I'm working on condensed matter physics, where the microscopic laws are well known. We know that you use non-relativistic. We know that electrons, that's Coulomb interaction. You need nothing else to explain the quantum Hall effect, superconductors. Everything can be explained with this input.
Okay.
But there are other phenomena like in liquids, Fermi liquids, there are non-Fermi liquids, Fermi liquids that don't behave the way Landau said they would. And it's been a challenge right up to now how to obtain those non-Fermi liquids from a microscopic theory.
Okay.
Don't just write it down. Can you deduce it from some underlying principle? That's one of the big challenges. And people are using all kinds of tricks from ADS-CFT, for example, to get non-Fermi liquids. Now, ADS-CFT originally was invented for a very limited problem.
Yeah.
But now people are using it for all kinds of problems, and I think it's fine. You can make any assumption you want. If you get results and they agree with the experiment, their assumptions are right. That's a new approach to getting, for example, one of the big questions is how to get Fermi systems with linear resistivity.
Okay.
That's not easy. If you take Landau's theory, you will always get resistance quadratic in temperature. Getting linear resistivity requires electron propagator to be very different from that of the free electron propagator.
Okay.
And so if you can say you don't like it, but what are you going to put in place of that? How do you get the non-Fermi liquid? So these modern techniques do give examples of non-Fermi liquids.
Okay.
That's one problem. What I did find I can work on is topological insulators. That, to me, is a wonderful example of a problem which has got features which are not independent of great details. Just like the quantum Hall effect can be understood with pretty much any system without going into details. You can get the quantum Hall effect, you can get the precise quantization of the conductance. That's why somebody like Laughlin is able to write down a wave function for some system that captures all the features. It may not be the system you have in the lab, but once you have a paradigm which explains all the features, you can take that to be representing all of them.
All right.
For topological insulators, they were lying in plain sight for many, many years. Nobody saw them. As you know, these are objects which are conducting in the surface, but insulating in the bulk. So if you take a blob, a cube of topological insulator, you attach wires to the surface, connect them to a battery, and you take an ammeter or something. The current will flow along the faces of the cube, but not in the interior.
Okay, I see.
And if you take a disk and attach wires on the antipodal points, current will flow along the circumference, but not in the bulk. So it's a very general result that in d dimensions, the bulk is d-dimensional and non-conducting, but the boundary, which is d minus one dimensional, is conducting. It's very interesting because you can ask yourself, why does that happen? Is it inevitable that there should be systems like that, which will always end up having a conducting state? What is it about the Hamiltonian that guarantees that? So they're called topological insulators because if you take the solid and you look at the band structure of electrons in the solid, the band structure is a function defined on the Brillouin zone, and you can map the Brillouin zone to the energy surface, and you can show that that is given by a winding number, a topological invariant, just like in the quantum Hall effect. That topological invariant is the conductance.
All right. Yeah. Okay, so another question. So the intersection between the general relativity and quantum mechanics is a hot research topic these days. So scientists are trying to find the theory of everything formula. So what do you know about that, and which approach between string theory, between quantum gravity would be the best one to pursue?
I think, first of all, string theory did explain a few things. I think one question they answered was, is information lost when you have a black hole, or is it somehow redeemable? I think the current understanding is that it is not lost. It is stored in the black hole.
And there's also Hawking radiation, which is important.
But they also found a way to, I thought Strominger and Wafar, somebody, tried to find a way to explain the entropy of the black hole, which depends only on the surface area. How do you calculate that? I think they found that using string theory, they're able to calculate the entropy that agrees with this great formula.
Okay.
So there's a way to count states and take the logarithm and get an entropy if you use string theory.
I see.
So that's a great feature of string theory. But You know, people say, why don't you test everything? I point out to people that the scale at which strings come into play is not only small distance, it's much smaller than you imagine. It's like saying that if you're studying the solar system as an astronomer, someone tells you you're looking at these big planets, but they're not just dots, they're actually huge objects. If you go there, you'll find they're made up of rocks. And the rocks, if you probe them, they're made up of atoms, and atoms have nuclei, nuclei have quarks. And to this guy studying the solar system, he doesn't give a damn about those things because it doesn't affect him.
Yeah.
But that's the level with which the world is different from what you imagine. It may be true, but you cannot verify it.
I see.
It doesn't make any difference to the physics at the scale you can probe, even if you're right. So that's the new situation we are in, where we may be right, but we may not know we are right.
I see.
Yeah, general relativity, by the way, Einstein had the responsibility to show what the predictions are.
Okay.
Otherwise, you can say it's a great theory, it's a great theory, is it right, is it wrong? Well, here are the predictions. I don't know how many predictions of string theory are robust or verifiable in that sense, other than the examples I gave.
But why Einstein didn't like quantum mechanics so much? He said that God doesn't play dice.
Yeah, first of all, I'm sure my friend Doug Stone has pointed out in his book, and it's known to anybody who reads the literature, that Einstein did not like, don't say he didn't like quantum mechanics because he didn't do the homework.
Right.
He did all the homework. He knew it better than anybody else. He used quantum mechanics even before Bohr used quantum mechanics. He knew all about it. And he was dissatisfied, and that is his right, given all that he has done. But I don't know if in its place he put anything that satisfied him.
I see. I see. So you think that is the reason why he maybe didn't like.
Yeah, you can say I don't like it. Whatever reason, you don't have to give a reason why you don't like it. He said I don't like the way. I think some of the arguments he gave, in the end, were very constructive because they showed you about entanglement.
Exactly.
So he tried to kill the beast, but he gave it a second lifetime because now the second quantum revolution has to do with entanglement.
Right.
So he involuntarily gave it a second wind in physics.
Yeah. And what do you think about quantum gravity? And why is gravity such a mysterious force in the universe? And do you think scientists will be able to explain, to apply quantum mechanics to gravity?
Well, that is the hope. I mean, string theory is one theory that does explain quantum mechanics of gravity. In string theory, gravity arises naturally. Any other way to put in gravity doesn't fit in. If you take any field theory and try to put gravity on top of it, you get all kinds of uncontrolled infinities. String theory, if you look at the list of what it does for you, is very, very amazing.
Yeah.
Witten said it's a theory from the next century. It dropped in our laps by mistake. We're like a bunch of apes staring at this monolith. We don't know what to make of it.
I see. What do you think are the biggest obstacles researchers are facing when they're trying to find the theory of everything? So, I mean, is it necessary to find the theory of everything?
People say you want a theory of something.
Yeah.
You don't want a theory of everything.
Okay.
So people are making progress with the theory of something every day. Like that's the theory of topological insulators. It's not the theory of everything, but it's a beautiful theory. In fact, doesn't even need interacting electrons. That's a surprising thing.
Yeah.
All these difficult problems involve electron-electron interactions, superconductors. But topological insulators can be understood in a non-interacting theory of electrons. Somehow people they missed it for many years.
I see. What do you think about artificial intelligence, and what do you think are its consequences on the humanity in the next decade?
You tell me. You're Mr. Quantum Information.
Yeah.
My son works with quantum information for his firm. Everybody uses it. He tried to put that into my head.
Yeah.
I haven't fully gotten a grasp of what it is. I have some idea of how it works, but I haven't fully understood. They put few things in a black box, and they don't tell me what's in the black box. I don't fully understand it.
I see. Okay. So, who has been your biggest influence on your academic career, on your teaching skills throughout your career?
I would like to say I had great teachers. I had two teachers when I was growing up. in India. When I decided to stop being an engineer and go into physics, engineering is the one all Indians wanted to do.
Yeah.
You get into the Indian Institute of Technology, you're guaranteed a job, you're guaranteed a lot of money, beautiful women will throw themselves on you, everything is guaranteed.
Right.
So I got into that Institute of Technology. After a couple of years, I read about relativity from a book my brother sent me from the US. Then I said, hey, what? This is amazing. Till that day, I had not been intellectually stimulated by anything in science. I was a good student. You tell me to learn this, I will learn this. Tell me to learn that, I will learn that. But I don't get carried away. That's the first time I wanted to learn more. So I didn't know what to do. So I had a classmate in the Institute of Technology, who was a couple of years ahead of me. He taught me basically all of basic physics.
Yeah.
We would go for a long walk, 1 hour walk. He would lecture to me. Each day we'll pick some topic. Statistical mechanics, he will first talk about the law of equal probabilities, then how to do the counting and how to get the entropy. Then I'll come to my room and I'll write up my notes and slip it under his door, and he will check it and he'll say, good, let's move to the next topic. So I learned most of undergraduate physics talking to him.
Oh, wow, wonderful.
Then when I came to Berkeley I left engineering and came to do physics. I was really anxious the first week when they gave us an exam to place me.
Yeah.
Because there are other kids who had gone to MIT and Caltech. They were in the same class, and I envied them because they had standard education unlike mine. But I found out at the end of that exam that I was doing very well, and it's because I took my own time to learn it.
Yeah.
I didn't rush through anything. If I didn't understand it, I took my time. I realized if you take a course in physics, it's not always a blessing. Just when things are interesting, a problem set is new. Then when it gets interesting, some other subject is calling you.
Right.
But when I did my physics out of the mainstream, I learned everything till I was satisfied. So I think that's a great way to learn. So I wanted to teach people the same way my ideal teacher would not use a blackboard.
I see.
I'll be able to talk to you and you can imagine in your mind what I'm saying.
Visualization, yeah.
Yeah. So when people come to Yale to give a seminar, I tell them, let's leave my office. Let's go for a walk. You tell me whatever you want.
Right.
That's how I like to learn.
Great way of teaching, yeah. So what do you think is the most effective way to explain complex scientific topics to a general audience? So people who are not physics students.
Right. I found out I could only explain 2 topics. I've given 2 public lectures in Aspen. One was on quantum mechanics and one was on relativity, because in all of them, there are some phenomena which can be explained to the audience. The double slit, or the fact that nothing goes faster than light. That sentence has the same meaning for me as it is for you.
Yeah.
But that's a limitation that is surprising. It's like thermodynamics. Nothing is colder than minus 273 degrees. That's a statement. You can understand what that means. But there is a deeper structure, but you can at least understand what's the new phenomenon addressed by this subject. So I could teach only these 2, quantum mechanics and relativity. I could teach in 1 hour. Just give them a feeling for what is the new physics. They cannot solve any problem. They cannot do any homework. They'll go away learning. For example, entanglement, you can say what the phenomenon is. That a measurement here has an impact on something far away from anything else. That's a fact. You can explain those things. So I found I could explain those subjects, but condensed matter is very hard to explain.
Yeah. Do you have any regrets in your career? Do you miss something that you wanted to do but you didn't, like a Nobel Prize or something
if I got a Nobel Prize, I will feel very uneasy because at least 1,000 people who deserve it more.
Okay.
I feel I've gotten what I deserve and maybe more. So I don't want any more. I'm quite happy with how I've been treated. Look, I left engineering and I came to this country not knowing much physics. And I could have ended up various places. I've ended up here in a university I like, with students are wonderful. I get to teach, I get to do research.
Yeah.
So I have no regrets. But some people tell me, why did you spend 5 years being an engineer? You could have left in the middle and saved a couple of years. Look, I'm now 77 years old. Okay, what if I'm 75? It makes no difference to me.
Right. Year
Right.
1 or 2, yeah.
But as an engineer, I learned a lot of things. Engineers don't bullshit. They when they say something, it should have an operational meaning.
Yeah.
This notion of scenarios invented by physics, engineers don't have scenarios. You build something, it's got to work.
Yeah, right.
That sense of values I got from the engineers.
And one of the last questions, what would you like to be remembered for?
Maybe for my teaching. I did some things in physics, maybe 2 or 3 papers which are worth remembering.
Yeah.
Others should be forgotten. But I'm glad I influenced a lot of students by teaching them. It's like being a parent. You haven't done very much, but you think your kids will do more than you will.
Right.
So my students are my kids, and some of them have done extremely well. And nowadays, with my lectures, I can reach students anywhere in the world, including people like myself 50 years ago trying to learn a subject.
Yeah.
Because internet is full of some good stuff and some junk, and if you can give them good stuff, you are doing something.
Right. And what are your plans for the future? Do you have some projects you would like to work on? For how long will you be teaching? And
Not for very long. Maximum 1 or 2 years is my guess. I don't want to put that on tape because then they'll close my office and throw away the key. That's what I'm thinking.
Do this.
It's very hard to step down. You can ask Mr. Biden what that feels like. But one day when you think you're not doing a good job, you should step down.
I see. Professor Shankar, that's all. Thank you so much for your presence, for your wonderful answers. I really enjoyed the interview.
Good. I enjoyed it too.
Thanks so much.
You are a very good. You come prepared. I like that.
Thank you so much. Do you have anything else to add for the end of our audience, for next, for your students or for any students?
Well, I have, one question people ask me, usually from India, is I'm an engineering student.
Yeah.
I want to do astrophysics. I want to do particle physics. I want to leave what I'm doing. They tell me, how do you do it? I tell them, you have to do a lot of hard work. You just cannot say these subjects are very sexy and they turn me on. No, baseball is beautiful. It doesn't mean you can be a baseball player. You got to see if you have the aptitude for it.
Yeah. So hard work beats talent, right?
I think so. In my case, it's absolutely true. 2 things. Oh, yeah, I should say one thing.
Yeah.
The one asset I have, I think, even to this point, is I try not to deceive myself. I want to make sure that what I say, at least I believe. If there is something wrong there, it's not because I know it's wrong and I'm still trying to peddle that.
Yeah. So we need to be honest to ourselves.
Yeah, that's the only choice we have. We cannot be smarter than we are. We can work hard and we can try to be honest.
I mean, we can deceive some people, but we cannot deceive ourselves.
Yeah, that's right.
That's the main point, actually.
Feynman used to say that you should prove you're wrong before others do it.
Right. Wonderful. Thank you so much for this phone call.
Okay, excellent. You're going to show me one day what you've done?
Yeah.
Okay, I will look at this and the other podcasts you have if you give me the link.
Yeah, of course.
Okay.
Thanks much.
All right.